So my talk will be on the glacial static adjustment contribution to sea level variations. It will be mainly a talk about the past, and when I say past, I mean only the last 21,000 years. But at the end of my talk, I will also look to present time. Present time, I mean the last century, and also to the future, the next century. I am from solid earth geophysics, so you will see some argument that have a lot of things to do with the solid earth. And unfortunately, I'm not an oceanographer, so you will not see many arguments about the seas, the oceans, and so on. So please be patient. And I would like to start with this nice philosophical discussion I came across recently. This was a discussion about the shape of the Earth in reference with the shape of the oceans. And this discussion was held in Verona, Italy, in the 13th century, just because there was a guy at the time in the town who put forward the idea that the shape of the oceans could be not really regular, not perfectly spherical. So the dispute was about the shape of the Earth and relative to the oceans, but also about the internal structure of the Earth. And the argument is that the spherical geometry is so perfect that all these things must be characterized by a spherical geometry. And internal anomalies were forbidden, humps in the water relative to the land were forbidden, and irregularities at a longer spatial scale were also forbidden. The reason was that the water is a perfect element and it should stay spherical all the time. Now we know that it is not the case, of course. We know quite well this figure. We know that land, the sea, geoid, and the ellipsoid are in general quite complex figures, have quite complex geometries, and we can accept very easily that the geoid is not regular, and in fact we know that there are undulations in the geoid. We can accept very easily that the Earth is not regular relative to the ellipsoid, and so on. So we accept this, and we accept also that on several timescales these figures are indeed changing. So what is the engine, for instance, at long time scales that maintain the geoid undulations? We know this figure very well, probably. These are the geoid undulation at harmonic D36, based on gravity observations, basically. These undulations are the offset of the geoid relative to the ellipsoid. And as you can see from this map, there are significant undulations, up to 100 meters, basically, that indicate a significant departure of this complex figure from a simple geometrical figure like the ellipsoid. So it was amazing seeing that there is no correlation at long wavelengths between these undulations and the ocean continents distribution, means that the engine of this long time scale process should stay in the middle of the mantle and not close to the Earth's surface. So this is indeed a very long time scale, and it is strongly related to the dynamics of the outer layers of the Earth, subduction, divergence, plate tectonics, and so on. And this pattern will change only when this pattern will change. It means very long time scale, millions of years. But we know that there are other time scales, in general shorter, also related to the cryosphere. And there are elements in the cryosphere which are changing the equilibrium of the solid Earth, and they are also changing the shape of the geoid. In this talk, I will be particularly focused on timescales of millennia, on the right side of this slide here, where huge ice sheets are melting and aggregating. And these huge ice sheets can perturb so significantly the equilibrium of the solid Earth to make, until now, very large deformations of the solid Earth that we can observe, and to produce during the melting period, means since the last glacial maximum, several regional sea level variations that can be observed by field investigations. But the cryosphere is a very rich system in which we have also smaller glaciers and ice caps, and normally, as you know, these glaciers and ice caps have also short time scales like century time scales and so on. In this case, it's very difficult to measure, to monitor the ground deformations produced by these ice caps, but with the aid of spatial geodesy, we can make observations that can measure the changing gravity field that is induced by the dynamics of these smaller ice caps. So what happens from a very simple physical point of view? Here on top you are at the last glacial maximum, about 21 kiloyears before present. These huge ice sheets were sitting on the Earth's crust until that time, and then some melting occurred, and this melting was so huge and intense that all the solid Earth were perturbed. The solid Earth is not responding as a rigid body, is responding as a deformable body. We can think at it as a very simple, in terms of a very simple mechanical analog in which there is an elastic response, which means that the Earth is responding exactly in phase with the surface loads, but there is also some viscosity. That means that the Earth responds in a delayed manner to the changing ice sheets. After the last glacial maximum, melting continued, and we are not here at present time. This is an intermediate phase in which rebounding is still occurring. The ice is reducing in volume, but we have at the same time a huge vertical deformation and gravity field variations in response to this process. What we observe now is in part, on a global scale, is in part related to this long-term process and in part related to the current melting of small glaciers. That's a cartoon that gives a very clear idea of the extent of the glaciers at the last glacial maximum, 21 kiloyears before present. Here there was a huge mountain of ice. Now it is almost completely disappeared. The thickness at the center was about 4,000 meters. Siberia was completely covered by ice, the same in Northern Europe, and many other glaciers on a global scale. So the amount of water was huge. The amount of water and the equivalency level variations implied by these dynamics was huge, and you can guess it by comparing the present-day contours with the gray ones here. That give you an idea of the amount of ice melt that we have observed during the last 21 kiloyears. So, in terms of equivalency level change, this figure has been shown already by Professor Barr this morning. We can measure. The first question is, what is the volume of water variation, and what is the sea level variation in terms of equivalency level? So we don't look at the regional response. We look at directly to the volume of water change, and we do it by making field investigations in sites which are quite far away from the places where the ice was melting, so to avoid some local effect due to the isostasy, local isostasy or regional isostasy. And as you see from this curve here, the melting was not uniform at all in time. There were meltwater pulses. The most important is probably 1A. And so we should not expect that the time history of melting when you have a given ice load on top of the Earth is very simple to describe in time, and you see the very complexity of this process. The equivalency level is basically a measure of the volume of the ice, and assumes that the sea level change is the same everywhere on Earth. And this is not exactly true, because there are many regional variations, and that's in fact the topic of my talk. The regional variations are due to a number of processes, and just to have an idea of the impact on a regional scale of what occurred since the last glacial maximum, I would like to show you this plot here, which is a snapshot. It is a modeled scenario. A snapshot at the last glacial maximum showing the extent of the ice according to ICE 5G, and the so-called paleotopography. Apparently, the shape of the Earth is the same as today, but if you look carefully, you will see that at that time, Australian mainland was linked to New Guinea and Tasmania. You will see that, for instance, Java and Borneo were linked to the Asian mainland, and you will see that there was a bridge between Alaska and Siberia here. So the face of the Earth was so different at the time because of the lower sea level at the time, but the regional response is already clear here. There were places where this effect is, there are places where this effect is quite small. There are places which have experienced a very large geographical variation. Also on the very small time spatial scale, like in the Mediterranean, these variations are quite significant. This is the face of the Mediterranean at the last glacial maximum. As you can see, the Adriatic Sea was completely different from now. There was a channel, not visible here, but there was a channel between Sicily and Malta, Tunisia had a different shape and so on. So all these things here are a consequence of melting, but not only of melting actually, because the Earth is responding in a very complex way to melting with vertical deformations, gravity field variations, and all these things are contributing to determine this regional sea level pattern. So an example from the Hudson Bay, we have several cases of observed relative sea level variations in this lapse of time between the last glacial maximum and present time. This is a classical example from the Hudson Bay showing that there are raised beaches that have evolved through time in response to the melting of the huge mountain of ice which was located in this place of North America and Canada. So here the history of sea level has been clearly dominated by a sea level fall relative to land during the last few thousand years. But from other places around the Earth, we know that this is not exactly the case as in the Hudson Bay. We have been working on the Mediterranean in the last years a lot, and we have found that, in fact, there are many different relative sea level curves across the Mediterranean. Examples here are given by San Vito Lo Capo in Sicily, where we have observed a sea level rise of about half a meter in 600 years. In Israel, sea level is basically the same as 2,000 years before present. In Mallorca, there is evidence indicating that the sea level variation has been quite small during the last 3 kilo years. And lastly, we went with Paolo Pirazzoli a couple of years ago to revisit the Roman fish tanks in Rome, close to Rome in Italy, where we have evidence that sea level has been rising of about 60 centimeters in 2,000 years. This is not the result of tectonic movements alone. This is the result of the glacial-static processes that provide a very complex regional pattern of sea level variations. So these patterns can be classified. This has been done in the past by several authors. This figure is taken by Kurt Lambeck et al. 2001. The classification amounts to define several regions in which the sea level curves have similar shapes. So the example from the Richmond Gulf in Canada was given before and is characterized by a monotonous sea level fall until present time. If you go to the Barbados, you will see a sea level rise with some jumps and accelerations. If you go in other places around the world, you will see oscillations, sea level ice stands, sea level falls, and so on. All these things can be associated with the glacial isostasy, and it is not, of course, a result of simply of tectonic movements. Do we have a theory to explain all these kind of very complex isostatic compensation process? The theory exists, fortunately. It is not mine. It has been written during the 60s and 70s. The theory has the target of predicting the relative sea level variations in response of ice thickness variation, and in terms of relative sea level change, means sea level observed in the reference frame of the solid Earth. So the red segment that you see here is sea level at a given time as it will be measured relative to the solid Earth, means virtually tide gauge. The question from a theoretical point of view, and it is the main question in this context, is can we predict the time variation of this red segment here, knowing something about the ice thickness variations and with some a priori idea about the Earth rheology. Actually, you don't have a priori the Earth rheology, and observing and using the modeled theory should help to constrain both the Earth rheology and the ice thickness variations. So actually, the system is a complex one, even if we don't look to the ocean dynamics. You have many physical interactions between the components of the system, which are the solid Earth, the oceans, and the ice masses. This figure is adapted from Clark and Lingo, 1979. You have a direct effect of loading between the ice masses and the Earth. You have load also between the oceans and the Earth. When the ice masses are melting, the oceans are changing their volume, and this extra mass will produce some loading on the Earth. The Earth will change its gravity field, and the changing gravity field will produce changing attraction between the Earth and the oceans, and the ice masses and the oceans. If you look to the bottom part, you have some unexpected loop also. If you allow for changes in the global shape of the Earth, you will allow also for some inertia variations of the Earth. You will consequently, by the second law of dynamics, change also the rotation of the Earth. But changing the rotation of the Earth will change the centrifugal potential, and this will change the geoid and so on in a self-perpetuating pattern. So all these things here are making this equation impossible. The equation here is called eustatic equation, in which sea level change is only a function of the volume variation of the ice masses. And actually the equation is much more complicated. It is shown here. I don't go into the details. They are provided by Farrell and Clark in 1976. It is an integral equation in which sea level change due to glacial isostasy is on the left-hand side of the equation, but it is also embedded in these three-dimensional integrals in the right-hand side. And the physical reason is that in order to have sea level change at a given place and at a given time, you should know the history of sea level changes at all the places at all the time before that time. Of course, you should also know the history of ice masses. So it is a formidable problem that has a lot of unknowns, if you want. We use this equation routinely to predict sea level variations in the past, during this century, and also to the future. So actually, we don't like these terms. They are too complicated, so for one moment we drop them. If we drop them, we remain with this eustatic sea level variation, which is saying that sea level change in response to a given volume variation of the ice will be the same everywhere. Actually, because of the presence of these four terms here, it will not be the case, and these four terms here reflect the complex physical interactions that I've tried to describe with the interaction diagram you have seen before. So is the theory in agreement with the observation? In the case of the Hudson Bay, like in this case, the agreement is very good, I would say. There is some misfit, of course, but we are very happy with this. It means that we have a theory that can reasonably explain, using some internal Earth parameters like its viscosity profile and so on, it can reasonably explain the past sea level variations. And this means that we have a good theory also for making prediction for the future. The agreement is not only good across the Hudson Bay. If you look to all the relative sea level observations that we have in this Tashingham and Peltier database, it is an old database, but still valid in my opinion. All the data are here in the form of a scatter plot. As you can see, these curves here have not a unique pattern, so we are not observing at all eustatic variations, but a much more complex pattern of sea level variation. And this pattern can be quite well reproduced by our modeling, in which we assume a given viscosity profile of the Earth. And of course, there is sensitivity in this. Changing the viscosity profile of the Earth will change the fit with the global set of observations. And that's why this theory is useful to constrain the Earth's rheological profile. So I have just a couple of points about the present times and the future. This century is a century of tide gauges. You probably know already this plot. It is a sort of summary, a stacking of the 23 record of tide gauges with the longest period during the last century. If you put these records together and you average, you get a sea level rise of about 20 centimeters in 1 century. There are some irregular features here, but the trend is quite clear. It is much more difficult to extrapolate a quadratic trend from this curve, however, but the signal here is so clear that demands some kind of explanation. What is the role of glacial static adjustment in this context? Apparently, glacial static adjustment should not contribute to the present-day sea level change because the ice aggregates of the Ice 5G model of Peltier, for instance, have already melted. So the average glacial static adjustment contribution to the present-day sea level change should be zero if averaged on the ocean surface, but locally it can be very important. It is exactly for this reason that together with these causes of sea level variations that we know already and have been described by Anny 1 hour ago and others, we should account also for the effect of glacial static adjustment at present time. This is a fingerprint that you obtain from the melting of past ice aggregates. This fingerprint has zero average on the surface of the oceans, but it has very, very, very large local effects. And without making a correction for these effects on the tide gauges that we have at our disposal, we cannot be able to guess exactly what is the average rate of sea level change associated with the climate changes presently. So the reason is that many of the tide gauges that have a better quality observation, means a long record, with small errors are from the northern Europe and from the coast of the United States. And these two places are greatly affected by glacial-static adjustment. So when we go to the newspapers and see estimates of the rate of sea level change occurring every year, here we have estimates by a number of authors ranging between 1.5 and 2.4 millimeters per year. This has not only been obtained by looking at the tide gauge observations, but this has been obtained, in fact, looking at the tide gauge observation corrected by the effect of the glacial isostasy, which have a very important role in all this stuff. So what about the future? I have a couple of slides about the fingerprints of future sea level change. This is a very short summary of the result base obtained within the Ice-to-Sea collaboration, which is a huge European project whose purpose was the understanding of the contribution of ice to future sea level rise. Our role in this project was to build ice scenarios for the future, and this has been done by a number of groups involved in the collaboration. So we have the distribution of ice elements, ice sources for the last 1 century in the top frame. These sources are coming from the surface mass balance of Antarctica and Greenland, from ice dynamics of Antarctica and Greenland, and from the so-called glacier and ice caps. These sources can be translated into future globally averaged sea level variations according to a mid-range scenario and to a high-range scenario. And the black line is the total contribution in the two frames, and the colored curves are the individual contribution from the top frames. So it is only in these terms, it is only an average scenario. Our role was to partition this scenario into a regional pattern according to the same equations that we use for describing the glacial isostasy from the past. So these are the fingerprints that we have obtained for the Greenland ice sheet from Antarctica and from the glacier and ice caps. As you can see, these fingerprints are very far from being uniform. The green line are actually showing the average of these fingerprints. That means the eustatic variations of sea levels that we would observe if the Earth were completely rigid and if we assume no variations in the gravity field, and the actual fingerprints are indeed very, very different from the expected average solution. So when we put everything together, we get this projection, this prediction for the year 2100 in a mid-range scenario. This shows the expected contribution to sea level rise from the terrestrial ice melt alone, so no ocean dynamics here. And as you can see, the pattern is very clearly zonal, which reflects the dipolar symmetry of the major sources of ice melt in the Antarctic Peninsula and in Greenland and in the surrounding glacier and ice caps. The mean is about 24 centimeters, with very large regional variations. So just to summarize, regional sea level variations are intrinsic in glacial isostasy, and they are caused by Earth deformation and gravity field variations, but they are also caused by the complex geometry of ocean floors and by rotational variations, time dependency of the ice loads, and also from rheological effects. Normally, when we solve these problems, we assume a steady state rheology, but it is only a model, and if there is some transient contribution from the rheology, this will, of course, add a new regional impact on these sea level variations. Future sea level variations are to year 2100 will strongly depend on the contribution of terrestrial ice melt, as you know. And I think that from the Ice-to-Sea project, we are now better. We have a better description of what the regional pattern of these variations will be. Sorry for the delay. Thank you.